first of all, if you have earbuds in, take your earbuds out. You can see them in your ears, so take them out and then listen to what I have to say, yeah. So when I ask you to show me that you can do the things that we've been working on with in class, you really have, there's only 3 things that you should be thinking. Number 1, okay, no problem. I know how to do these things because we've been working on them, and you want to see me execute a task? No problem, I got that. Number 2, okay, I'm not quite ready right now, but I know what it is I need to do, and I will be ready, and so I'll show you later. Number 3, I'm hopelessly behind. I have no idea how to do any of this stuff. I need help. It's going to take me a little bit more time than you might expect, but I've got this. Those are really the only 3 things that you should think. It shouldn't be a case that you feel nervous. You shouldn't feel like, oh, this is gonna, like, I'm gonna get you. I'm not looking to get you. It's really simple. I want you to be able to do stuff. If you can do it, then show me. If you can't, then figure it out. If you need my help, then ask me for my help. This is not like your other classes and your other school, where the goal is to put you through the ringer and make you suffer, and then put you on the spot and make you feel bad if you didn't get it in time or didn't figure it out in time, or entice you to maybe use somebody else's work, or lean on somebody else, or just flat out cheat. I don't want that. I know you can all do this. I would say about 70% of you have figured it out. You understand, oh, he's asking me to be able to do something. I know that I can do it, and so I'm just gonna do it. When he asks me to do it, I'm gonna do it, and we got this. Some of you have still not figured it out. Some of you are thinking of this as a test that you need to pass, and you're trying to play a game. And the game is, I'm gonna do as little as possible, right up until the moment that I'm gonna be tested. And then I'm gonna try to figure it out as quickly as I can, because that's but that's regular school, and this isn't. Here are the things that we've been working on, and we've been working on these for a while. Maybe you figured them out already, maybe you still need help. If you still need help, that's what my job is, okay? The things that we're looking for you to be able to do, can you work with free body diagrams? Can you make them, and can you use them? In any situation at this point, I ought to be able to say, there's this object, here's how it is moving, here's where it is, here are the things that are supporting it. You should be able to draw a free body diagram showing all the forces acting on that object. How well can you use static and kinetic friction? We did a bunch of work with friction. We have the model of friction, which says that the force of friction is always going to be equal to, or in the case of static friction, less than some coefficient, some stickiness coefficient, times the squishing force between 2 things. That's the normal force. How well can you test and revise a predictive model? What? We've been doing that this whole year. That is what we've been doing. We have been making predictions and then testing them. And we'll talk about it today with regards to the cart accelerating along a horizontal track. And how well can you evaluate empirical data? Empirical means observable, it's not just a matter of opinion, it's not just your thoughts, it's actual observations. How well can you evaluate that data? Those are the skills that we've really been focused on here. Embedded in this idea of free body diagrams are the concepts and the equations and all the stuff that we did involving weight and normal force. We've done a whole bunch. And here's the thing that I want you all to understand is it's complicated. There is almost nobody in here, and I include myself in this, who couldn't get fooled. If I were to throw a very specific scenario at any one of you, I could trip you up. That's not my point. You could do the same to me. And I actually would encourage you to do that. Not because I want to prove you wrong or humble, make you feel humble, because I would love for you to see me get tripped up. I would love for you to see that happen so that you realize, oh yeah, this stuff is just like, there is no way that anybody can like figure out all the possible scenarios in advance. You just can't. You draw a picture of something and say, what are the forces acting on this thing? And somebody can come up with a way that you're wrong. Somebody can be like, I didn't say it was on Earth, haha, there's no weight. And then maybe there's like less of a normal force than you thought. Or there's all sorts of like ridiculous little tricks that we can play on each other. But given a somewhat straightforward situation, we all now have had time to work on and think about how to talk about the forces acting on that object. What I want is for you all to use these next couple of weeks as an opportunity to figure out what you know, figure out what you still need to learn, and then show me that you've got these things mastered. Okay, these are the things that are gonna be evaluated over the course of the next 2 weeks of school, and everybody in here can do this. Everybody in here can do this with no stress. It doesn't need to be stressful. It just doesn't. It, as crazy as it sounds, if we did school right in a general sense, this would be fun for everybody. Every single person in here would not only recognize that this isn't stressful, but you would find it to be a fun and interesting challenge. And if there's anybody in here who doesn't, it's not your fault that you feel that way. It's our fault for setting up school in such a way that it makes you feel like you're constantly being evaluated and compared, instead of thinking about school as an opportunity to practice things that you're already good at, learn things that you haven't learned yet, which is really how it should be set up. So the three things that we're gonna do today is, and two of them are gonna be primarily me, and one of them is gonna be primarily you. I'm going to really quickly walk you through the work that we did with the horizontal acceleration of a cart. If we have a target acceleration, how do we get there? That is only one kind of problem that we can look at. I will then go through the homework problem, which is a different kind of a problem. In that case, we're asking a totally different set of questions, but you'll see there's a lot of similarities. And then we'll start working on the final Newton's laws and forces related activity, which is, I just call it the accelerating carts lab report, and in this case it's a slightly different scenario. It's not a horizontal cart, and there's something in front of the cart, so there's some things that we need to take into consideration that we didn't before. All right, so before I get started, does anybody have any questions? Okay, so let's start with looking at the horizontal carts activity that we were working on the last time I saw you, which was ages ago. So the basic setup is this. You have a track that's set up horizontally. You have a cart that's being pulled by a string that's looped over a pulley, and there is a hanging mass on the other side of it. And I call the cart N1 and the mass N2, but it doesn't matter what you call them, there's no magic to these letters. M1 is simply the mass of this object. Even if it wasn't a cart, we could still call it M1. M2 is the mass of this object, whether it's a sack of bricks or one of those tiny little hanging masses that I provided for you. And so what I have said a bunch of times is that we have a system. And part of what is going to get you the skills that you need to demonstrate to me is practicing using that system. So here's part one. Make a drawing and establish a frame of reference. So I'm going to say that my axes are perfectly horizontal and vertical. My positive is going to be to the right. Up is going to be positive as well. And it's just going to be X is horizontal and Y is vertical. Okay? That is arbitrary, but you're used to this. And you'll see when we do the homework and when we start the final lab, there is a part that you're not used to. There's a way of thinking about what we're doing that isn't going to be as familiar to you. We've done it, but it's not as familiar to you. okay? So that's step one, make a drawing, establish a frame of reference. Step two, make free body diagrams. Free body diagrams show each object that we care about. Sometimes there's one, sometimes there's two. Theoretically, there could be 25, but in this case, there's two. We have two things that are moving, they're connected together, they're each experiencing forces. So the forces that our cart is experiencing, we know that there's going to be tension from the string to the right. We know that it's going to be experiencing a friction force to the left. How do we know that? Not because of the drawing, and not because every time we have this situation it's experiencing a force to the right from friction, but because I told you it's going to be moving this way and accelerating in that direction. If both of those things are true, then there's going to be a force of friction in the other direction. There has to be friction, always opposes motion. Okay? So we know it's going to be accelerating this way because that was the goal. I said, what do you need to do here to get this to accelerate to the right at a certain rate, 0.2 meters per second squared. And then I said, it's assume that it's moving this way. Why? Because it could be moving the other way. There is absolutely no reason that we couldn't engineer a situation in which this cart starts off moving to our left. If it's moving to our left, then the force of friction is going to be in the other direction, and this free body diagram isn't accurate anymore. So sometimes you have to know. You have to know. If I tell you there's a car on the street and it's moving, and I ask you what direction friction is acting on the car, you cannot answer that question unless you know what direction the car's moving. You have to know. You have to. So in this case, we know it's moving to the right, so friction is to the left. We know that there is a gravitational force and a normal force acting on this cart because we know it's not accelerating at all in our vertical dimension, which is our y-axis. We know that these two forces are going to be equal and opposite to each other. It turns out in this particular case, they don't really matter. We don't care, we won't care about them, but that's not always true. Sometimes we do care, all right? So there's one of my free body diagrams. Here's my other free body diagram. It's for the second object. This doesn't have any horizontal forces acting on it. It has a gravitational force pulling it straight down, and there is tension in the string. And I'm going to add something to my previous free body diagram, which is that this mass is m1. This is m2, right? We have two different masses, so there isn't just one weight in this problem. There's two. The force of gravity is pulling down on this mass, and it's pulling down on this mass, and it's pulling with different strengths. Okay, one of these objects is going to weigh more than the other. And in this case, you can see the way that I've drawn it, it kind of looks like the weight is bigger, the magnitude of this downward force is bigger than the magnitude of this upward force, and that's true. It is going to be bigger. How do I know that? Well, I know that because our setup is that the cart is accelerating to the right. If the cart is accelerating to the right, and this whole thing is like set up the way that we're looking at it here, then this mass has to be accelerating down. If the cart is accelerating to the right and the mass isn't accelerating at all, or is accelerating up, then funny things are going to happen with our string, right? Like it's gonna bunch up if the mass is not accelerating down as the cart accelerates to the right. That string doesn't bunch up. We know that's not going to happen. I mean, it would if I like put my hand underneath the mass, but then the cart would stop accelerating. So to get this cart accelerating at a constant rate, we have to have a constant tension in the string, and for that to happen, the mass has to be accelerating down. If the mass is accelerating down, then this downward force has to be bigger than the upward force. That's how forces work. The combination of forces determine the acceleration on an object. In this case, if we have an object accelerating down, it has to have a larger downward force on it, okay? And then the next step is to take these forces that we've drawn and look at them relative to our frame of reference. And if there are any forces that aren't either aligned with our x-axis or our y-axis, then we have to deal with them with trigonometry. And because this was sort of a starter, we didn't have anything that we needed to deal with. Everything here is either perfectly aligned with our x-axis or perfectly aligned with our y-axis, okay? The next step is to apply Newton's second law to both of these objects separately. For the cart, we have two equations that we're going to think about. One is that the sum of the forces on this cart in our x direction will equal its mass times its acceleration in our x direction. We have one force in the negative direction. We have one force in the positive direction, and that's going to equal this cart's mass times its acceleration in the x direction. We also know that the sum of the forces on the cart in the y dimension will equal its mass times its acceleration in the y dimension. We happen to know in this case that it's not accelerating at all, so that has to be 0. There's one upward force, so that's in our positive direction. There's one downward force, and that is going to equal 0. In this case, we can determine that the normal force acting on the cart has to be equal to its weight, and that's not useful in solving the problem that's been set up here, but it is true, okay? And then for our hanging mass, the sum of the forces in its x dimension will equal its mass times its acceleration in the x dimension, but there are no forces in our x dimension on this hanging mass. There is no acceleration either. 0 equals 0. We don't get any useful information from that, but our y forces will be equal to its mass times its acceleration. That means the upward tension force plus the downward weight will equal the hanging mass's mass times its acceleration in the y dimension. And there's a couple conventions that I have been emphasizing that are tricky. These I doubt everybody's gotten yet. It takes practice. You just have to practice, 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 practice. And that convention is that when we talk about forces, all of our variables stand for positive numbers. So that means this force of friction is going to be a positive number. This tension is going to be a positive number. I have a negative sign in front of this positive number, so negative force of friction plus positive tension is going to equal mass times acceleration, okay? In this case, we know the normal force is going to be a positive number. The weight of this object, mg, is a positive number. And some of you have been asking, wait, but isn't g negative? No. G is defined as the magnitude of the acceleration of an object in free fall. And B, there is no negative. There's no such thing as a negative acceleration or a negative velocity, or negative position, or negative force. There's only directions. We use positive and negative as shorthands for directions along one axis. It's like left and right. Which is negative, left or right? What do you think?
Whatever you decide it is.
Whatever you decide it is. There is no positive or negative built in to left and right. There's no positive or negative built into up or down, or this way and this way, or this way and this way. There's just one direction and the opposite direction. As soon as you tell me, oh, left is going to be negative, then I can tell you right is positive. If you tell me that up is negative, then I can tell you down is positive. If you tell me that this direction is negative, then I'll tell you that this direction is positive. But what you can't do is say G is negative, because there is no guarantee that anyone is going to be using a reference frame in which there is an axis that we're considering that's perfectly vertical, where the downward direction is the negative direction. Okay? So G is defined as positive, and objects weight is a force of gravity acting on that object, which means it's a positive number. There's no such thing as a negative force, but this force is in what we've defined as the negative direction, okay? And then with our hanging mass, the tension is going to be a positive number. It also has weight. That weight is a positive number. Because it's in the negative direction, when we add the forces together, we put a negative sign in front of it. One force this way plus one force this way is going to equal the difference between those magnitudes. If we call one positive and one negative, we add those two things together because one is up and one is down. One is left and one is right, or one is this way and one is this way. And so that's our convention for forces. The variable always stands for a positive number. What does that mean? That means if it's a force in the negative direction, we put a negative sign in front of it. What does that mean? That means when we do the algebra, once we've set up our equation, we just manipulate these numbers as we would any other algebraic number, any other variable. And whatever we get, we get. We're always going to find that if we try to find the magnitude of a force, we're going to get a positive number because that's our convention. If I want to find the tension in the string, I'll solve for tension here and I'll get the tension equals a positive number. If I want to find the normal force acting on the cart, I will find that the normal force is equal to a positive number. That's the convention that I've set up. When I follow that convention in setting up my equations, I get what I expect. Forces that are always positive. Now here's the problem. Our accelerations aren't forces. This acceleration is unknown sometimes. Now in the case of this particular setup, we know exactly what the acceleration is because we have a target. We want it to be 0.2 meters per second squared to the right. We know that. But sometimes we don't know, like in the homework problem I'm about to solve for you. Sometimes we just don't know, and that means that we have a variable here that could be to the right, or to the left, or up or down, or one way or the other. We don't know. So when we're looking at velocities, accelerations, positions, and some other quantities that we haven't talked about yet, like momentum, now we have a different convention. This might be positive, or it might be negative, or it could even be zero. We just don't know all the time. In this case, we do. In this case, we know what the acceleration is, but in many cases, we don't. What will the resulting acceleration be if you apply a force this way to an object along with another force this way to an object? You don't know what the acceleration is until you find out. Same with this acceleration right here. This acceleration might be positive, it might be negative, and it might be zero. That's not the same convention as for our forces. With our forces, we assume the forces are always going to be a positive number because we know what direction they are. We already know their direction. So in our free body diagrams, when we draw an arrow in one way or the other way, we can decide, well, this is going to be my positive direction. And now we know what the positive force is in our positive direction, or our positive force is in our negative direction. But with acceleration, we don't know. So with this particular setup, the way that I've got everything arranged here, my cart will be accelerating in its positive direction, while my hanging mass is accelerating in its negative direction. Okay? And everything else is known here besides the unknown mass, right? So we know the force of friction that was given in the problem. We know the mass of the cart and our target acceleration. That allowed you to find the tension in the string. I don't remember what it was, and it doesn't matter at this point. Once you know the tension in the string, you know that the hanging mass needs to accelerate at negative 0.2 meters per second squared, and that allows you to find the mass and the hanging mass. I'm not going to do that algebra again just to save a little time, but that is doable. I did it for you a couple weeks ago, and I'm happy to show you individually again if you need to see the algebra. This right here is the entirety of the predictive part of this. Everything else is arithmetic, right? Like, and you might have made mistakes. You might have made arithmetic mistakes. I could easily make an arithmetic mistake right now. But this setup, it describes everything that we need to know to make a prediction for how much mass we need to hang right here in order to get this whole system to accelerate at the proper rate. Now, the next step is to set it up and test it. And what you probably found was that it was not great. Some of you found it was pretty close, which is really neat. And I mean, that's ideally how physics works, is we're able to make predictions that are reasonably close. But others of you probably found, oh geez, that was, I was like pretty far off, and that's fine too. What happens next is the testing your prediction, evaluating your data, and then making changes to your setup or making changes to your prediction so that you can get closer to reality. And we're not going to worry about that for today. That's going to be something that over the course of the next couple weeks will unfold. All right, I'm going to pause this for a sec.